So welcome everyone for TCS Plus. We're very happy to have Ewin Tang today. So before I introduce her, let me first thank the organizers working behind the scenes to bring you these talks. So that's Anindya De, Clément Canon, who's with us today, Gautam Kamath, Ilya Rosenstein, and Oded Regev. So thanks everyone for that. Let me also go around the table and introduce everyone. So first, we have Ben Lee joining us with a group from Caltech. Hey, Ben. They're just like a couple doors away. Then Clément Canon from Stanford. Then there's Jian Chang with a group from Penn State. Welcome. Jonas is joining us from Istanbul. Are you okay? I guess you're in Istanbul right now. Okay, that's cool. Thanks for joining. Joshua Grochow is joining us with a group from UC Boulder. Then there's Santiago. Oh, well, Joshua, let me mute you. Sorry. Okay. Then Santiago joining from EAFIT. Welcome. And Simon joining us from ERIF in Paris. Welcome, everyone. That's a big group. Thanks for joining us. Okay, so we're very happy to have Ewin Tang give the talk today. So Ewin completed her undergraduate degree at UT Austin under supervision of Scott Aronson, and now she's working towards her PhD at the University of Washington, supervised by James Lee. So I just learned a few minutes ago that Ewin was named on the Forbes 30 under 30 list this year, which is very impressive. So we're very proud to I think this might be the first time, I'm not sure, at TCS Plus. So she's going to tell us about work with Seth Lloyd and Andras Gilyen that was part of her master's thesis, or undergraduate, sorry, research thesis, if I understand it correctly, that will also appeared at Stock 2019. And so welcome.
Thanks for having me. This work is actually, so the original work is like a different paper. It was like basically the same topic. This is kind of like an extension. I'm going to be talking about a similar result that builds off the techniques. But yeah, thanks for having me. Thanks for everybody for showing up. So I'm going to be talking about my work in quantum-inspired classical linear algebra algorithms, and basically sort of like why you would think to work on, or like to learn about these algorithms and sort of how they work. So all of the stuff here is going to be classical. So technically you don't need any quantum background, though most of the motivation will be like solely in quantum. So presumably like you might want some like quantum interest or some quantum intuition if you want to understand where these algorithms are coming from. And along the way, feel free to ask any questions. Like I can't see anyone, so I can't really judge whether people are following or not. So it would be very appreciated if you could ask questions when you're confused about things. The idea is that we're going to start high level and then gradually introduce more and more sort of complexity, and hopefully everybody can gain something from this talk. That's the goal. Okay. So let me start by giving like the broad takeaways, the sort of main points of this talk. The first one is that there are unexplored parallels between quantum linear algebra and classical randomized linear algebra. And these parallels between these fields is sort of the bread and butter of the research I've been doing, and has led to some interesting discoveries about sort of when quantum machine learning can produce speedups. And indeed, this brings me to the second takeaway, which is that there is a good framework that can analyze whether quantum machine learning algorithms can get theoretical speedups, or like quantum linear algebra algorithms can get theoretical speedups over classical algorithms. And it's not exactly obvious how you would do such a thing, at first glance. So this is kind of an interesting notion that I want to put forth. And finally, using this framework, we can get the intuition that you won't be able to get exponential speedups from quantum machine learning by looking at low-dimensional data, or at least this framework seems to suggest that conclusion. And so hopefully I'll elaborate on all of these points during the talk. Okay, so one of the sort of like holy grails of quantum computing is finding exponential speedups for problems that people care about. So, the most obvious example of an exponential speedup given by quantum is Shor's algorithm for factoring. And well, it's not a proven speedup. Like, we don't know that for a fact that the quantum algorithm is exponentially faster. But there's some just like heuristic, there's some we believe basically that it is exponentially faster. And so this has sort of led to a lot of research in quantum algorithms to sort of figure out, well, is there anything else that we can exponentially speed up using quantum computing? And so one thing that I didn't put on the slide here is like quantum simulation, which is like very promising. But we're going to be focusing on like classical tasks, or like basically standard algorithms tasks. And there hasn't been too much, I would say, progress on this. Like there have been some like proposed candidates, but nothing super that seems like close to being resolved. But this paradigm is where quantum machine learning comes in. So the elevator pitch for quantum machine learning is that it gives exponential speedups for just a variety of machine learning and data analysis problems that software companies care about. So there's this huge list of literature that sort of applies quantum to various machine learning problems, and then sort of claims exponential speedups, or at least, you know, they give sublinear algorithms for these machine learning problems. And obviously, if quantum computing could speed up machine learning exponentially faster, then this would be basically like revolutionary for software companies, and like it would basically change the way that we do machine learning. So this is a pretty important thing, or I guess this is an application with a lot of hope, I guess, in terms of like what it, if this held, what it could be used for. But the issue is that these exponential speedups come with caveats, and I'll focus on one, what I would characterize as one of the main issues, which is that all of these algorithms assume that you have some quantum input. So this is in blue. So they assume that you have some quantum input, so input as a quantum state, and then it gives the output as some quantum state. And so here we're representing we're looking at vectors as quantum states, and then we're able to do linear algebra to them. But the question is how you even get these states in the first place. If you're given your input vectors in quantum states, then you can do a lot of things in time sort of exponentially faster, I guess, like polylogarithmic in input dimension. But sort of in order to prepare these states, you need to have some regime in which you do this. So on the left side, I give a few examples. You could assume that your input vectors are in some type of quantum RAM data structure, or you could like assume that they're sparse or close to uniform or something of this nature. And there are a lot of ways that you could implement such a state preparation procedure, and they all give different sort of qualitatively different outcomes in terms of what the algorithm actually does. And the same goes for the output. So for any sort of, you get your quantum state as output, and then what you do with that is kind of left to you to decide. And so, you could feed it into more machine learning, more quantum machine learning algorithms, or you could just measure the output quantum state or do some sort of swap test. But it's on you to given this output vector, try to learn what you want to learn about it in efficiently. And so this is well and good. The main issue comes in when you want to actually analyze, okay, how useful are these quantum machine learning algorithms, and namely how what is their actual speed up in comparison to classical algorithms? Because if for each choice, for any particular choice of like how you want to what you assume about your input and what you want from the output, then this defines a corresponding classical problem of like corresponding classical problem with like the same input and output. And because state preparation is a non-trivial assumption, you're making your problem easier by assuming these things from the start. So what this means is that there's not though these algorithms give exponential or what seems to be exponentially faster algorithms, they also assume some things that is not clear. What is the best thing to assume? What's the best thing to assume for practical usage? And so this is where a model comes in handy. And this model is sample and query access. So the idea is that for the settings in which you can prepare states corresponding to input vectors efficiently, you can also sample according to a distribution defined by these vectors and query to their entries. And basically, you have some stronger access to the input vectors than just being able to read them in. And the interesting thing here is that this model seems to be pretty broad in that it allows you to it's a comparison that works for a surprising number of cases in the quantum machine learning literature. Basically, the argument being, given any instantiation of your quantum machine learning algorithm with classical input and classical output, you can also perform a corresponding instantiation with sample and query access. So I'm being a little bit ambiguous, so I'll define what I'm talking about. The general idea for the framework is that if we have a quantum machine learning algorithm that assumes state preparation of the input, then we want to compare this to classical algorithms that assume sample and query access to the input. And so the premise here is that if we have a routine for any particular setting for efficient state preparation, then this leads to, then we can find an efficient way to simulate sample and query access. So this is sort of like the premise for why we would care about this model. And so this means that if this premise is true, then if there's no exponential gap between these two theoretical models, then there's no exponential speedup in practice. Basically, if you believe in this premise, understanding sample and query access, classical algorithms with sample and query access, is a good proxy for understanding the classical capabilities of algorithms in any particular setting that you can also perform quantum machine learning algorithms. Does that make sense? Are there any questions so far? Okay. So what do I mean by sample and query access? So if you have query access to a vector, then I'm defining this as being able to find the entries efficiently. So one way that you can get query access to a vector is if you just store that that vector in your RAM in an array, in which case you can just index into the ith entry of the array in order to get the ith entry of the vector. And obviously for like your standard classical RAM, this is an efficient operation. And correspondingly, sample and query access is this query access. However, in addition, we assume that we can efficiently sample from the vector. And what I mean by sample is we output an index with probability proportional to its entry. So we output the index I with probability xi squared over the norm of x squared, so proportional to the value squared. So this is what you would get if you measured the quantum state corresponding to x in the computational basis. And finally, we assume that we have its norm somewhere, that we have it stored. And this last one can sort of be weakened, and we will denote the SQ with the asterisk as this sort of weakened version. But it's sort of you can be pretty rough with this estimate for the norm, and it'll be fine.
So I've got a small question here. So the approximation is only for the norm, or also would you can we weaken the sampling as well to say you sample approximately from that distribution for some good notion of approximately, or does that break things?
It should work. I think usually in situations where you approximately sample from something. So let's say that you sample from x, but you have epsilon error in total variation distance. I found that usually you can rephrase this as just saying that you sample from some y, and then y is close to x in 2 norm. So usually you can rephrase these things in terms of a sample and query access with only error in norm. And then I guess you move the error somewhere else. But yeah, you could definitely do that. I know that you can, if you assume multiplicative error for the probabilities, you can definitely, everything works out fine. Total variation distance, I'm not quite sure. Okay, so the reason why sample and query access is kind of seems like the natural comparison to quantum algorithms with input states is that it sort of seems to appear in places where it seems to you seem to be able to perform these accesses whenever you're able to prepare quantum states. So for example, in QRAM, the standard data structure for preparing a quantum state corresponding to V will also give you sample and query access to that vector V. So this is the reason why the recommendation systems, quantum recommendation systems algorithm was could be dequantized, for example. And we'll go over that later. But I'd also like to point out that this works for other settings in which you can efficiently perform state preparation. So in the setting of sparsity, of V being sparse or V being close to uniform, you can also do this fast sample and query access. And so it's if you're able to think of like a general class, like a large general class of vectors for which you couldn't perform state sample and query access, but you can perform state preparation, this would be kind of interesting to me. So yeah, I'm not aware of any such things. So, but these would be cases where the premise is not true. And so in most cases, in the cases that I know of, this seems to hold. Okay, and so elaborating on this QRAM relationship, this we're able to instantiate sample and query access using a dynamic data structure. So you might notice that this data structure here, this binary search tree, is the same one that you would use to prepare the quantum state to do your state preparation as well. But yeah, so I'll discuss the sample and query access part. Okay, so this data structure, so this proposition says that there's a data structure that supports sample and query access in logarithmic time. And what this data structure is it's a binary search tree, as you can see in the example here. And at the leaves are the entries, and at the interior nodes have value just the sum of the two children. And so you can see that at the top there's the norm. And so you can see that because this is a tree, you can do lookups for your query access, and you can find the norm. And you can do all of this in logarithmic time. Sampling, how that works is that, okay, to explain this, I'm going to use a specific example. So here I've just put in some numbers for a particular vector x. And what I do is I recurse to sample from x. I will start from the root node and then randomly recurse on a child with probability proportional to its weight. So for example, here I start with the root, and then I recurse on the left side with probability 2/3 and on the right with probability 1/3. And then so if I recurse on the right, I do it again, and I recurse on the left and the right with the appropriate probabilities. And at the end, the index, sort of the output that I get, will have the desired distribution. So you can sort of see this. When you multiply the probabilities out, you get 1/4 as desired. Okay, so are there any questions about this data structure?
Well, I was wondering if you can perform a Grover search on the database.
Sorry, move up what?
Can you perform a Grover search on the database that you have?
Yeah, so actually, so if you have that, if your xi's consisted of 0s and 1s here, then in fact the root node is just the number of 1s. So So you can see that if you just recurse down and then you keep making sure that the nodes that you're looking at have non-zero value, then you're eventually going to get to a non-zero entry. So right, so this is like an important thing to remark, which is that in this setting where we're assuming state preparation access, and sample and query access, Grover searches, searching is no longer hard. So the whole reason that we can do linear algebra quickly is because we can find areas of high weight in our matrices and vectors. And so these parts of these portions that are heavy weight will matter the most when performing linear algebra. And so that's why we can do things in sublinear time, or I guess polylogarithmic time. Okay. Now, I'm also going to define sample and query access to a matrix. And what this will be is, so I'll define if having sample and query access to an n by n matrix as having sample and query access to the columns of the matrix, as well as a tilde. So a tilde here is the vector of column norms. So the ith entry of a tilde is going to be the norm of the ith column, the 2 norm of the ith column. And just from the way I've defined it, it follows pretty straightforwardly that there is a data structure that supports sample and query access to A, to a matrix. And what you do is you just take the data structure for a vector, and then you just do that for all of the vectors that you need to do. And it turns out that this will give you a data structure that has similarly nice properties, namely sample and query access in logarithmic time. Okay. So now we'll move on to what's possible in the sample and query access model. And so this is going to, we're going to here discuss the techniques that are used to dequantize low rank quantum algorithms. So this is includes recommendation systems, supervised clustering, principal component analysis, and this low rank SDP solving. So all of these were originally quantum algorithms that assume some sort of low rank structure about the input. And then people were able to dequantize these into corresponding classical algorithms that are only polynomially slower. So basically showing that these quantum algorithms, assuming that you believe in this sample and query access model, don't provide exponential speedups. And from now on, we're going to assume that all sample and query accesses take O of 1 time, just for simplicity. If you want, you can assume that they also take O tilde of 1 time and replace all of the big O's with big O of tildes. And then we'd be using a data structure or something like this. But that's not necessary for the results. Okay, so so what's one thing that we could do with sample and query access? Well, it makes computing inner products easy. So if we have sample and query access to X and query access to Y, then we can estimate the inner product between the two in time independent of M and N. And how you do this is, well, you have the ability to sample. So the naive thing to do would just be to sample. And once you get the index from the sample, you define a corresponding random variable. And the way that you define this is such that the expectation of it is the inner product. So this is what it needs to be. It needs to be this expression. And then the expectation will be exactly what you want, the inner product of the two. And its variance will be the norm of x squared times the norm of y squared. And when we have this random variable, then we can just take a bunch of independent copies of it and then take the average to get an estimate of the inner product. And if you take 1 over epsilon squared samples in your mean, then you'll be within epsilon times norm of x times norm of y additive error to the desired value. So there's also this a standard trick in randomized algorithms which is to take the median take log 1 over delta medians of these means to improve your failure probability. So this is what we're doing to get the 1 over epsilon squared log 1 over delta result. So notice that this is a situation. If we had x in a quantum state, then we would be able to compute inner products with a swap test. And in the classical setting, without sample inquiry access, computing inner products would require linear time. Estimating inner products would require linear time because you need to find a non-zero entry. But with sample inquiry access, you can perform similarly to the quantum algorithm and actually just estimate the inner product as desired.
Sorry, I've got a pretty dumb technical question. So here, why do you use this, like the basically Chebyshev instead, and then median of means instead of just using Hofding-Chernoff to begin with? Is there like some advantage in doing that, maybe like pairwise independence only, or is it just because it's pretty much as good anyway?
You don't have a bound on the magnitude of z. So z could be like z could be large, and I think that prevents you from using Hofding-Chernoff. Am I correct on this, or?
Yeah. Anyway, that
Does that seem right?
Yeah. Thanks.
Okay. Yeah. So you can think about this as like, since x is like arbitrary, since your input vectors are arbitrary, then these can be basically any distributions. So this is sort of why you need something like the median of means. Okay, so so this inner product thing appears a lot in it helps a lot in dequantizing algorithms because you can sort of apply it to a lot of generic things, a lot of more general settings of high order tensors. So I'm giving one example here, where instead of estimating the inner product of vectors, we're estimating the inner product of two matrices. So I have sample inquiry access to A and then query access to B, and I want to compute the trace of A transpose B, which is sort of the notion of inner product in that setting. And we were able to get the same result here. These are Frobenius norms instead of two norms. And we're able to do that just by noticing that the trace of A transpose B, if you write it out, it's just the sum of Aij, Bij for all ij. And this is just the inner product of two vectors, so the flattened versions of A and B. And you'll notice that if you have sample and query access to A, then you have sample and query access to the flattened version of A. And that the norm of the flattened version of A is the Frobenius norm of A. And then so you can just apply the inner product result, black box, to get this result. Okay. Another thing that you can do is to compute sort of what I call thin matrix vector multiplication. So the setting here is that we have a tall vector v. So here we're thinking of k as like constant, and n as being large. So it's a tall matrix, and we have a vector, a small vector w, and we want to compute. We want to get sample and query access to the product VW, and this is just a linear combination of a small number of vectors. And the algorithm that we're going to use here is rejection sampling, and I've written out what it is here. Essentially, we sample a column proportional to its corresponding weight in the sum. So we want to sample from this sum, and so we sort of guess at what this distribution might be by sampling a column proportional to the weight and sampling an index from the corresponding column. And so this is our guess of what we want. And then we accept it with a particular probability, and then otherwise we'll just try again. So here, this is going to be the expression for the probability that you accept, and you'll notice that this is you only need to look at Vij for a particular value of I, which means that this only takes k queries to compute, and so each iteration takes k queries and O of k queries and samples. And for this algorithm, you can compute that the probability that you output I on some iteration is going to be this expression. And the probability that you output anything is going to be this second expression. And what you want to output is you want to output the probability that you want that the probability that you output I after everything is completed is VW I squared divided by the norm of VW squared. And so correctness follows just by noticing that the probability for any particular iteration, the probability that I output I given that I output at that iteration is going to be the probability that you want. So this will imply that the distribution that you output is correct. And the previous, the probability that you output anything on a particular iteration, 1 over that is the number of iterations in expectation. And so this is the expected number of iterations, which means that the expected runtime is this value. Now, if you ignore the k squared, what's left here is basically like a cancellation constant. So basically, so if you think of V as being, the columns of V being like orthonormal, then this cancellation constant is just 1. However, if VW happens to be much, much smaller than any of the columns of V or any of the coefficients of W, then this constant will blow up. This makes sense because if you're trying to sample from a vector and the vector is really small in comparison to what the input is, then it's going to be hard to find in the vector. So you need to sample more to try to find it. So what I've described is a method to sample from VW in time independent of M and N. So this constant here in all of the settings that we'll talk about will be independent of M and N. Querying and computing the norm follow from similar. You can also get them from this procedure, and in particular, querying is easy. So this gives you sample and query access to the thin matrix vector multiplication. So we'll try to remember these two routines of inner product and thin matrix vector because they'll be used throughout the rest of the talk. Okay, are there any questions about the routines? Okay. So now we'll move on to low-rank matrix inversion. Okay, so first I'm going to define the singular value decomposition of a matrix. So if we have a rank K matrix A, then the SVD, or singular value decomposition, is just going to be a decomposition of A into U sigma V, V transpose, where U and V have orthonormal columns, which is equivalent to the statement that like these products are the identity. And sigma is a diagonal matrix. And so if this is a singular value decomposition, then we're going to define the pseudo inverse, which is we denote by A plus, as being this V sigma inverse U transpose. And so this the pseudo inverse of A acts as its inverse on the image of A. Or I guess it's a natural definition of the inverse for a low rank matrix that doesn't actually have an inverse. Okay, and what'll be useful is the singular value decomposition represented as a sum of K rank 1 matrices. So here the UI is the columns of the UIs are the columns of U, and the VIs are the columns of V, and the sigma i's are the diagonal elements of sigma. And so here I'm just rewriting this decomposition in this form, and correspondingly the pseudo inverse in this form. So here the subscript is going to denote the singular value decomposition that it comes from. Though for A, we're going to skip. We're going to ignore this. Or I guess the UIs without a subscript are going to denote the ones that come from A. Okay, and so what's the problem of low-rank matrix inversion? Well, the idea is that we get a matrix A, an m by n matrix A, that is rank, that has low rank. So it has rank at most K, where K is something that we assume to be small, like polylog in the dimension. And you assume that it is, so we assume that it's sort of well conditioned on the subspace that it is on the space where on the space where it's defined, or I guess on its image, I guess, and say that it has condition number kappa. Either it sends vectors. I guess the way to say this is that the singular vectors of A are between 1 over kappa and 1. Okay, and we're also given a vector B, and we want to estimate a pseudo inverse B. And we want to estimate it to sort of additive error, and additive in terms of the norm of B, not the norm of a pseudo inverse B. Because here, if you, for example, basically this is so that if a pseudo inverse B is super small, it can be like very small, and so we don't want to we want to ignore the cases where it's too small to measure accurately, and then we only want to consider the cases where sort of A pseudo inverse B is like similar to the size of B, and then in which case you get a multiplicative error. Okay, so for this problem of low-rank matrix inversion, there's a quantum algorithm by Grebentrost et al. That basically says that if we can prepare some quantum states that correspond to the vectors, or I guess the rows of A, and we can also get the quantum state corresponding to B, then we can produce such an X in a quantum state. And this recent work that's joint with Andreas Gilyen and Seth Lloyd, and there's also a similar result by 3 postdocs at UT Austin. This result basically says that you can dequantize this by replacing sample and query access, or sorry, replacing quantum states with sample and query access. And in fact, you don't even need sample and query access to B, just query access to B suffices. And so this is an example of a dequantization of a low-rank problem. And so in specific, this is what the statement of the result, which is that if we have sample and query access, I'm going to say sample and query access to A transpose. This means that we have sample and query access to the rows and not the columns. And query access to B. Then in this time, so this time is independent of the dimension, or I guess polylogarithmic in the dimension. Then we can simulate sample and query access to X, where each query takes this amount of time. So basically, we can compute some description of X, and then getting sample and query access to X from the description takes this amount of time. Okay, and then the rest of this talk will be devoted to sort of proving this. Is everything clear about sort of the statement of the problem? Okay.
Just a quick question. So in the statement here, you say you can simulate sample and query access to X. Is there like some amortization in the running time, or is it for each query you have to pay this? Is there a chance you can amortize if I promise you I'm going to make 1 million queries to X to amortize some of that?
Well, okay, you can think about this first runtime. This first runtime as being what happened as the result if you don't amortize, and the second result is as the one that you get when you do amortize. So querying is actually a pretty easy operation. So the runtime for querying is less than this. I sort of ignored it in this statement of the theorem. But basically, the idea is that you pay this one-time cost, and then for each subsequent query and sample, you pay this amount. Yeah. Oh, and this sample and query access should have an asterisk. You get approximate value of the norm. Okay. So we'll start off with a warm-up, which is what happens if we know the SVD of A. So what I mean by this is that suppose we have sample and query access to U, to V, and to sigma. Well, sigma is k by k, so it's like very small. So we only need to assume query access to this. And what if we replace sample and query access to A with sample and query access to the components of the singular value decomposition? So in this setting, here we can write A pseudo inverse B as this sum here. What I did was I took the expression for A pseudo inverse as with the SVD, and I just multiplied it by b. And so you're able to factor out this inner product here, namely. So that's the only thing that's different about the thing that I showed before and this thing here. And okay, how do we sample and query from A pseudo inverse B? Well, first, what we could do is we could estimate all of these inner products. So there are k inner products of for each inner product of ui with b. And for this inner product, all that we need is we need sample and query access to a column of u. So we have this we have this here, and query access to b, which we have. And so we're able to estimate these inner products. And now with this estimate, this sum becomes a small linear combination of VIs. So we know we can compute this inner product over sigma I. We can get the coefficients. And so now we just need it to compute to sample and query from the linear combination. And so we can use the second result of thin matrix vector multiplication, which requires sample and query access to the V's, which we have. And it requires you to know the coefficients. So this query access requires the estimates from before, along with the query access to sigma. And so in this way, we can get from these sample and query access to the SVD, the sample and query access to A pseudo inverse B. So in sort of this way, we can sort of build together these pieces into a larger, into like more sophisticated results. So is this like small, I guess, toy problem clear? This. Okay. Well, for the problem of low rank matrix inversion, obviously we don't know the singular value decomposition of A. But we can actually get pretty close. We can find out a lot about it. So this is starting to get a little bit more technical. But if we have sample and query access to the rows of A, or I guess A transpose, then we want to find we want to get information about the singular vectors of A. And one way to do this is to think about the product A transpose A. And so the eigenvalues of A transpose, the eigenvectors of A transpose A are going to be the VIs, or the right singular vectors of A. And we can write this as a sum of AI transpose. So this is a sum of outer products corresponding to each row. And you can think about A transpose A as basically being like a sort of like a tensor, a sort of like some sort of inner product. If you think about these A's as being ordered to tensors, I think that's the right thing to say. But literally what we can just do is use a variation of the inner product protocol and say that we will look at R transpose R. And what R is just going to be a sum of these outer products. And these outer products are going to be the rows of A, just like rescaled and sampled. So we're just going to try to sample for the important rows to look at, and then look at the corresponding sum of outer products. And so namely, the expectation of A transpose A is the same, or sorry, the expectation of R transpose R here. Oh, I'm sorry. There should be a normalization term here. There should be something like a square root of S or something here. But the expectation of this should be A transpose A. And when you do this, you're able to do this because you have sample and query access to or I guess the row norms. You have sampling query access to this A tilde that I mentioned before. And using this, you can get R such that R transpose R is close to A transpose A. So you can prove this result about that these two things are close. And this is slightly less trivial than the inner product thing. I think to get the best values, you need a martingale inequality. But this result has been known for about 20 years in the randomized linear algebra literature. So this is like approximate matrix multiplication type result. And so because we have this, we get that the corresponding singular vectors, so this VR, is close to VA. And I write it like this because the singular vectors aren't actually individually close together. It's that they're subspaces. The subspaces that they define are close. And this is what this means. And further, the singular values that we get are close. Okay. Now, this means that it suffices to compute the singular vectors and values of R. And R is S by N. And N is still like a lot. But what we can do is we can actually subsample columns. It should say columns. We subsample columns of R and basically do the same thing that we did before. Using sampling query access to A, we can actually subsample and get a matrix C that's S by S. So now it's really small, such that the left singular vectors of C are close to the left singular vectors of R. So in this way, we sort of shrunk our problem from an M by N problem to an S by S problem, and that one's tractable. So then we can actually compute the corresponding singular vectors and values. And then V hat here, which we define to be this expression R transpose U C sigma C inverse. This will basically be our proxy for VA. So I'm running out of time, so I'm going to skip over some of the details. But here's what we get in the end. After we perform this sort of subsample and querying for computing this singular value decomposition of C, we get sampling query access. In the end, we get what we had before, which is sampling query access to A and query access to B. But we also get sampling query access to R. So we get this because if you recall, the rows of R were rescaled rows of A. So we can just use sampling query access to the rows of A to get sampling query access to the rows of R. And so we can actually get sampling query access to R. And we also had the U and sigma that we recovered from the singular value decomposition of C. And here I'm denoting the bold to mean these are the dimensions that we should worry about. So these are the ones that we want to not incur in our runtime. And so here I've brought back the expression for A pseudo inverse B as this sort of inner product before. And now we can't get this product exactly, but what we can do is we can approximate it by this V hat, which you recall was defined in this way, and we can show behaves sort of similarly to the singular vectors of A. So here we're approximating VI by V hat I, and UI by A V hat I. So this means that we actually incur another sigma squared here. So this should be sigma squared. And if we write out sorry. if we write that out, it should be it'll be R transpose times this expression here. And if we come back to this, then we get an inner product of we get the same thing that we had before, which is basically we got an inner product on in the coefficients here, and then we have a thin matrix vector multiplication on the outside. Yeah, sorry, this is R transpose U here. Should be U. And so the inner product here is VI transpose A transpose B. So I'm referring it to it as an inner product because it's actually this inner product that we had before, which is this A transpose B V hat I transpose. And in order to apply that result, we needed sample and query access to A and query access to this second vector, which is the outer, which is sort of an outer product. And we can actually get those. So the ones that are orange here are the ones that we would need for, are the ones that correspond to needing the sample and query access to A and to the query access to B. And getting query access to V hat requires using these three. But it's, you can do this naively. There's nothing going on here. It's just that this is actually a small sum. So you're not looking at the long parts of this matrix. You're looking at the short dimension. Secondly, this thin matrix vector product that comes from here, what you need is you need the sample and query access to R. So we have that. And the query access to this expression. And here, again, we're using the estimate for this. So all we really need is the access to the sigmas from here and the U, which we have here. And so we can get sample and query access to the output. So this is the end of the algorithm sketch. The rest is just analysis to show that the approximations are sort of in the way that you want them to be. Okay, so to conclude, there's still a lot of open questions. There are still some quantum machine learning algorithms that I think it would be interesting to dequantize. And I think it would be interesting to see whether you could break from this low rank restriction at all in terms of how these dequantized algorithms work, and more importantly, I guess, how quantum machine learning algorithms sort of how the difference between classical and quantum when it comes to data that isn't low rank. Another open question is that a lot of the quantum algorithms have these like log 1 over epsilon terms, and these terms don't tend to. So you often don't get these terms when you're sampling in classical computing, and so it would be interesting to see how these whether you can actually get these terms in some situations. There's also closing the polynomial gaps. So if you recall, the exponents of this theorem were pretty high. They weren't great. And so figuring out actually the polynomial speedup that you can get would be interesting for because it's possible that you could still get something out of quantum machine learning even if you don't get exponential speedups. And finally, I think this is just the understanding what you can do in classical computing is just a good way to do better quantum algorithms, quantum algorithms research. And so I think that's an important thing. Okay, thank you.
Thank you.
Are there any questions?
I can can see Clément walking towards the laptop. I don't know if that's a question. Otherwise, I have a question. But... Okay, let me ask my question while the others are coming up. So can you go back to the open question slide, just like one slide? So here, so just, I mean, this is a very general question, but so your algorithm works in the low rank case. So just the most basic quantum machine learning algorithm, so the HHL algorithm. So that is slightly more general, right? So it works in, I think sparse is fine, and then maybe it's even more general than that. So just make sure I understand. So there's a gap between the two there, right? So there are cases where HHL applies, but your algorithm doesn't. But somehow these cases are not cases for which we'd have an interesting application to a machine learning task. Is that correct, or?
Right. So yeah. So HHL, the standard instantiation is with like assuming that A is sparse and well conditioned. So in this setting, you probably can't get corresponding classical algorithms because HHL is BQP complete.
Okay.
So I guess the reason why you would consider low rank matrix inversion in the first place, or sort of the reason that this low rank assumption crops up, even though you could do things without the low rank assumption, is that whenever you get your output, whenever you get your output, you want it to be something meaningful that you can sort of get information from. And if you compute A inverse B for something that's like well conditioned, this means that it's not clear in what settings A inverse B is a meaningful thing to sample from or to compute inner products from. Because since it's so high dimensional, if any guess for how you would measure this would probably be wrong. I don't know if I'm being clear, but basically, you know, if A is well conditioned, then you know you might expect A inverse B to look kind of uniform or like random for a lot of data that you might consider. And so the low rank assumption is helpful for the output. And it's interesting whether you could like find a better way to recover things from the output.
Thanks. Do you have other questions? I think there's no questions. I'll take us offline and we can continue the discussion there. Let me just announce that 2 weeks from now, next talk will be given by John Wright from MIT. And so let's all thank Ewin for the talk again. And I'll take this offline, and then, but if anyone wants to hang out and ask more questions, then you're welcome to stay. Okay, thanks a lot.
Thank you.